Hi, everybody! It's Joe from Joe's Computer Museum. I'm in a weird mood today. Deal with it. Anyway, welcome to the stream. Before we get started, I just want to note that this can of Diet Coke spilled all over here just before stream. So I'm in a great mood. Other than that, how's all your Sunday going? So, I wanted to work on some keyboard encoders. So I just finalized the design of a replacement keyboard encoder for very early Apple IIs. And I wanted to get one built on stream and show you the build process of that and give you some ideas of how I do that reverse engineering process. And then I was challenged, was it last night or the night before? I don't remember. I was challenged to reverse engineer the keyboard controller for the Amiga 500. I'm like, okay, so maybe we'll do that tonight and have some fun reverse engineering a keyboard controller. I don't know how far we'll get, and it might be a little boring because it's a lot of like connecting oscilloscope to pins and stuff and figuring out how the controller like does things. So we'll see. The upside to the Amiga is that I have a full data sheet for the chip that they used. I have a full data sheet for how it was connected to the Amiga, and I also have the key matrix for the Amiga. So I have most of the data that I need. I'll only need to actually like tap the data line and press keys and figure out what data it's sending out and do a lot of typing and logging what the key sequences are. But other than that, there you are. So, housekeeping. Thank you all for stopping by. We only got a few people in the chat tonight. It's kind of a random stream, but we've got Rudy and John. Hi, Rudy and John. 2 concurrent viewers. Well, that's cool. Remember to hit like. If you're not a subscriber, hit subscribe. Those things help YouTube to show my channel to people who watch other stuff that you watch that might not see my channel. Basically is how that works. So, yeah. That is how that works. You can follow me on the Twitters up here, up there, that thing right there. If you're not a follower, I'm sure the 2 people who are on the stream watching me right now are, but that's fine. You can also go to my Patreon. You can go to patreon.com/Joe's Computer Museum. Drop $1 in the cup. It helps fund the operation and keep things going and, you know, replace the cans of pop that I tip over and pour all over the place. So without further ado, we're just going to get to it. Now, I kind of just randomly started the stream up with absolutely no preparation at all. I'm like, I need to put something on my channel. So if you want to hang out for a second, I'm going to get my second camera up and running so you can see what I'm doing. Doesn't take long. I click that button. I click this button and I click that button and we do that and that's correct. And I click this and that is up and going. And now you can see all of this stuff down here. That's great. Cool. The camera stopped for some reason. Did the phone rebooted? This phone randomly reboots, so it'll come back eventually. Reed Reinfeld is here. Yes, Joe, I would send you a case of Diet Coke, but it's Canadian. Javier's here. Hi, Jav. Yes. Random viewer. Yes. So this camera will come back up online momentarily. I can probably change to this other camera. Do I have the overhead cam? Why is that not working? That's nice. Okay. There it is. There is bench cam. I don't usually like using this camera for just reasons, but because I can't get it close and whatever. But so here's my little test setup I got going on here. So this keyboard encoder is a replacement for, if it will focus. Is it going to focus? You going to focus? You going to do it? The MM5740AAE, which is a replacement for, and I have it down here. It's a replacement for the really, really, really old Datanetics keyboards for the Apple IIs. So this was sent to me broken. It actually wasn't as broken as I thought it was, but that's not really important. But it allowed me to actually put together an encoder chip and test it in a real keyboard to make sure it worked as it's supposed to. And it does! It works great. So I've spent the last, I don't know, week or so putting together this test frame here. Basically, it's just a test. It's a keyboard, just using these little push buttons. Because this keyboard down here that I just showed you isn't mine. So I have to send that back to the owner. So I ended up creating this test frame that directly mimics the original keyboard so that I can actually, when I build these for sale on my website soon, I'll have a frame that I can put these in and actually test to show that it works. So that's a thing. Let's see if we can get this other camera going real quick. Yep. Stop. Stop. Close. Reopen. I like this other camera better. Start. There it is, working now. We can now switch to that. That's a better camera. I like that camera much better because you can actually see things. Adam's here. Hi, Adam. Yes. You're researching the initial timing and total timing should be for your 383 big block. Fun stuff. So, yeah. So I've got this whole setup here. So we're going to actually plug this encoder in, and I'll show you that it works. And it works really, the encoder works great. This silly keyboard doesn't because of ground plane issues. But it works well enough for me to test it. So that goes in the socket. And this goes right in that, like that. And then we can put you over here, as long as I'm very careful with moving this because the power connector's wonky. Got you over there. So I can press 1, and it boots. Now you're going to see a lot of key repeats when I press these buttons to test it. Because, like I said, there's some ground plane wackiness going on with this. Yeah, see the O does it and whatever. Yep. The N is the worst. I don't know why. It repeats even though it shouldn't. But it only repeats in this. It doesn't repeat in an original keyboard. So I've got a test frame for testing these keys. So, yeah. Yep. That's that. So I, as part of the deal for getting the opportunity to borrow that keyboard, I am to provide the owner of the keyboard 3 of these. I got 2 built and 1 partially built. So we're going to finalize building this last one real quick. And then we'll get to the piece of resistance, or whatever you want to call it. We can start actually reverse engineering the other key. I would love to see a video on how you reverse engineer a chip. Well, you know what? You know what, Rudy? You're about to have it, because that's basically what we're doing today. So let's switch over here. Let me rearrange my windows here so I can see things a little better. That works a little better. I have better control. So we can go to Scope Cam with Bench. So we can get on onto here, and we can put this together. So here is Mr. Microchip. Now I have already soldered this guy on. I did that earlier today. I was actually doing that on Justin Morgan's stream. He was making up one of these things right here, and I hopped on and I finished up one of those during his stream. That's the bottom of the chip with the or the replacement with the chip already on there. There's the top of the chip, and I've got the pull-up resistor. Actually, those are pull-down resistors on there already, which it requires, because the original chip has built-in pull-downs, but this microchip does not. So yeah. Oh my gosh. Would you look at that? Somebody did a magical thing, and they did a magical thing. Can I do the thing? 1999 super sticker. That's crazy. Thank you, Mac Effects, Mark. What he's really doing is he's giving me money to try to get me to finish the Apple IIc keyboard. I'm still waiting on final code for that. That's why that's not happening yet. One of our partners in crime helping us design that keyboard has a little bit of an illness right now, so he can't give me the code, but that's okay. So I'm going to show you the trick of how I build these little like chip replacements. So basically, first off, you can see here, maybe you can't, I have basically a socket that's soldered onto a little piece of perf board that I use as a assembly frame. So that's how I do that. And then my PCBs are the same size as a 40-pin chip or whatever chip, but with just these plated through holes, right? But it's got to have pins just like a chip does. So what I do is I use these little Arduino headery things like these, and I put them through the holes, solder them on the, and then put them to where they're all the way through so that they're same length as an original chip effectively. And then solder them in, then cut off the tops. And when I do that, that basically allows us to be, the thing ends up being the same size as an original 40-pin chip. It's a little bit shallower. And it does the thing. So, yeah. You're like, no, it's because you're awesome and you reverse engineering stuff is fun. Thank you, Mark. You're awesome. Mark is a sweetheart. Thank you very much, sir. So let's go ahead and get these in. Like I said, I've already done most of the work on this. So I'm just finalizing this assembly to show you kind of what my encoders look like. And, you know, to give myself free advertising for my own encoder that I just finished designing, which will be on sale on jcm-1.com very soon. I need my solder, and I need to turn on my fume extractor. Okay. So we just take those and we bend them over like that, right, to get them out of the way. And then I can just solder them in place. Just like that. Sure that's fully soldered. No stragglers, please. Cool. And we take our side snips and we cut them off. Rumor of a new Apple III card. Yeah. I am working on some Apple III stuff as well. Those are all snipped and out of the way. That's awesome. So then we go down here and we do it again, and we do this 40 times because there are 40 pins. And then once we get all the pins in, and I'm going to clean, you can see I've got flux junk on there still. We'll clean the chip up, and I'll show you how I program the chips. You can even do a quick walk through the code so you get an understanding of how my code works. It's mostly original with some hints from a couple of places. Basically, I took some hints from some other code, not direct code copy or anything like that, just hints on how it should work and stuff like that. Pins, pins, lots of pins. Hi, Justin! How you doing, dude? Thanks for stopping in. I know there's a lot of streams going on tonight, so everybody who's decided to come hang out with me, I do appreciate it. I appreciate all of y'all. You're all my friends. Okay. Lots of pins. Now, this chip is a little bit weird, too. My first batch of these, my first PCBs, as is always typically the case with me in flipping PCBs, is it had a couple missing traces. Now, luckily, these traces were only power and ground, and luckily, they were easy to tap onto. So each one of these, as you can see, I'll put the finished one here, has a couple bodge wires on it. Yep, so the first run of these will be bodge wired, but that's okay. Goes in there like so. More solder doodles. Rudy! That's crazy! Wow! Thank you, Rudy. Woo! Appreciate that, man. Yours is going to stay up on the screen for a while for that one. And Justin says, thanks for stopping in to give us the story of the lead bright. Yeah, that was a cool story. If y'all want the story of the lead bright, I could tell it here, but I'm not gonna. I'm going to give you guys the opportunity to go back over and when you're done here, watch Justin's stream, give him some more stream hours. I hop in fairly early on the stream, and I tell you the story of how the lead bright works, of how it came to be and why it happened. It's a very interesting story. So we do that. One last set of 4 pins on the end here. There's that. Good soldering practice as well. Yes, the lead bright is like, oh, you want like to do 100, or wait, there's 512. Oh, I'd say there's about 500 and maybe 530 total joints on that thing if you fill out the entire thing. So yeah, if you want soldering practice, it is a good thing to do soldering practice. However, I am all out of lead brights. Run number 1, which lasted for 2 years, is done and gone. There's no more. I may do another run eventually, but I don't have immediate plans on that. So those pins are all in there. So now we get to do some connected doodles. So I'll have that ready. So what we need to do is, this is the ground pin here. You can't see it. This is the ground pin. And it needs to connect to this pad right here. That one. And right next to this ground is power, which is right here. The power pin right here, and actually it's up here. Power pin up here needs to connect to pin 32. So 2 is ground and 32 is power. And wouldn't you know it, I just have the perfect tiny little wire for doing that. So we're going to do that. Do the thing. I'm going to show you my trick for tinning these wires. So basically I let it hang off the edge of a little surface so I can get at the edge of the wire, and I use a little bit of blue tack and I stick it down to hold it in place, right? And then I get my iron and my solder, and I just smother the end of that wire, and it just whoop, burns right off and does it. Cool stuff. Now I don't need that much on there, to be honest, because I only need a tiny little sliver like that. Now this has got to go into this via hole right here, just like that. Goes into that via hole. We fold it over flat. Put our little blue tack on there so it doesn't go anywhere, like that. And then we zoom in. Will the lead bright kit V2 have animation so we can do Amiga boing ball rotation? That would be cool. Now, a lot of people have asked me over the years, can you animate it? Can you do this? Can you do that? And I had started working on a design to do that. But the thing with that is that there are basically pre-existing things out there that are already 16 by 16 LED arrays that are fully animatable, that have all of the features you're asking for, and are like $25 on like Amazon and stuff. So yeah, no, somebody's already done it. I can't compete. Why would you buy mine? We could just go to Amazon and buy one, right? So that's in there. We can come back out of Super Zoom. And this one goes to pin 2, right up here, just like that. So we can Do that. And we can super zoom way in again. Enhance, enhance. I love this microscope. It's nuts. Garth is here. Hey, Garth. How you doing, sir? So we just smother the heck out of that till it actually like burns the stuff away. Takes a little work. Just being belligerent. Stand by. There we go. Cool. So that's done. Get this, can lob this little spike off the end of this here. Cool. Just snip that guy off. We do a quick beepity beep test to make sure that it connects. It's got continuity between the wires. You can't see it. What is it covered with? It is covered with enamel, or more specifically, it's like shellac. It's shellac varnish. It's a natural enamel. Okay, and so I put one right there on that pin, so you can see, or right here, I should say, right there on that, and the other one up here. And we got beepity beep beep, and it's good. So now that's the negative terminal. So now we do the positive terminal. Exact same process, different pins. So we're gonna tin the end of our wire here. Ah! Don't do that. A little bit more. And the wire is tinned. Now that one goes right here. In that one. Zoom on down on that. Raspberry. It is not raspberry jelly, no. The tears of the ancient unicorns. Yes. So way down in here. There we are. That's in there. And then this one goes over the pin just above the resistor, is how I remember it. That's my mnemonic. Get off there, blue stuff. Nope. So basically, this one goes right to that pin. Maybe it's Reefa goo, yeah. Okay, so we're going to tin the tip of this one. I'm going to do it a little differently than I did the last one, because the last one didn't work as well. So we're going to do it this way instead. Perfect. If you get it from the end, you get right at the metal that is exposed at the very end of the wire where you've cut it, and it allows the solder to get right to the wire and heat it up and burn off the stuff faster, in my opinion. Get that kind of turned on there. Gonna hold it with my finger very precariously. Not recommended process. There we are. Just like that. Easy peasy. Super duper. So now we test this. 18 people watching. Hi, all 18 people. Ah, I just broke my multimeter. Stand by. There they are. Make sure that this talks to that. It does, and it's not cross-connected with any of these other pins. Nope. It's not cross-connected with the ground. Nope. Cool. That's done. So that chip is made. Hi, Curti Unlisted. How are you? So now we're gonna clean it. Switch back to that. So we're gonna clean this real quick, using several different little bottles of chemicals and things. This noisy thing no longer needs to be on. Cool. So let's see here. Let's do, first off, we're going to just use a little bit of paper towel, a little bit of my PCB solution, which is 1/3 alcohol, 1/3 Windex, and 1/3 ultrasonic cleaner solution. Just use that to kind of get the surface gunk off. Okay, all clean a doodle there. Turn that a little bit so you can see me working. Okay, then we're going to flip it over and do the back side. Backside looks pretty clean. There's some goo. There's a little bit of goo in there. Just a little bit. Yeah, just a tiny bit. Cool. Awesome. That looks pretty good to me. Close enough for practical purposes. Okay, so that's this one. This is this one. This is the blank one. Cool. Now you guys get to see how I program stuff in 1/3 tapioca. You're funny. So I need to click this button, go to Facecam. So there is the completed chip right there. All done. Now we need to program it. So I'm going to show you my programming setup. It's kind of nutty. So what I have is I use the PIC16F series of chips. When I got the PIC16F, I needed a programmer for it. It was one of the first programmers that I ever purchased for anything. And so I did a lot of research, and I found that they had this little kit that you could buy called the Curiosity HPC, or High Pin Count. Would you focus on what's actually in front of you and not, are you focusing on that? I don't know what it's focusing on. Focus on the actual thing. Anyway, right here, the Curiosity HPC. It's designed for 28 and 40 pin PIC microcontrollers. And it came as a kit with a PIC, with an actual PIC chip, the one I needed, surprisingly, for like $38 back in the day. It was crazy. It was way cheaper than any other programmer out there for the PICs at the time. So I just went with this. Yeah, it's designed as like a creation kit. It's like an Arduino kit sort of type of thing for doing PIC microcontrollers, but it's just as like, okay, I can just use it as a programmer. I don't need to use the rest of the stuff. So that's what I did. Now, it doesn't normally come with this zip socket thing on there. I put together a zip socket. I kind of soldered together a whoop-de-doo there, right? I soldered together the whoop-de-doo so I could put chips in it. Processing. Now, this was for, because I did a lot of my early programming on the 40 pin dip chips, the big ones. But I since graduated to surface mount. So I need a way to program these chips after I've assembled them. So I've created these little adapter doodles that will, you can see the wires underneath there, that will connect wherever the programming pins for that chip end up being on this layout, and then wires them to where they're supposed to be on this. So I can zip socket into the zip socket like that. And so I've got this funky stack. And then I put the chip, the assembled unit to be programmed in there like that. Right? And then I hook it up to the computer. I do. So let's do that right now. So give me a second, and I will show you the program. I've gone through this program before in the past, way long time ago, for the JCM1 computer, because it's effectively the exact same code I used to create the keyboard for the JCM1, and I've just modified it, changed it over time. So let's do this thing. I need to go to this button and move this over here slightly and do screen cap right. Yes. So now you can see my magical code. Yes, you can. So it's a little hard to see, but here's the programming code. So all this stuff at the top is just generic. Here, let's set up the PIC microcontroller to do things. It's like it just sets up the programmer and your frequencies and just a whole bunch of stuff. I define what the pins are so that I can know. Basically, what these defines do is it creates an alias of this name that I'm saying is equal to this actual pin on the microcontroller, which allows me to take one set of code and rearrange the code to match where I'm rearranging pins around for different projects. So this one single piece of code with a couple small changes can support just about any keyboard controller out there. It's pretty cool. So I've got all this defines and blah, 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 stuff. Main variables and things. That's all boring stuff. It's C programming. You have to predefine everything. So here's the main loop. That's it. Basically what it does is it scans down each row of X's. It activates an X line. Then it checks each Y line to see if a key is pressed. Basically, it turns on an X pin, and then reads the value of the Y pins. And if the Y pin is a 1, that means it has voltage on it, which means it has received a pulse to do the thing. Effectively, that's how that works. And so basically you're completing a circuit. And then it's got some extra stuff. This one here, it's got a delay. Here it is. So basically what it does is if the key is pressed down, it sets a little flag so it knows it's been pressed. Then it checks to see if it was pressed the last time it came through this loop. And that is an automatic debounce, effectively. When you press a push button, the button vibrates a little bit, and it will, at the speed of electronics, will turn on and off a whole bunch of times. It go, and that can trigger multiple key presses. Well, you don't want it to trigger multiple key presses. So what I do is I basically check to see if the key was down the last time it came through. If it was down the last time it came through, which it checks right here, then it knows that it actually has to send the key data out, and that's what this does. And then this is just some other stuff to handle the key repeat process. This keyboard controller repeats the keys, or repeats the key press if it receives a pulse on a specific pin. It doesn't auto repeat. In the old Apple IIs, you had that weird repeat key, which you had to press to repeat a key. That's just because that's how this keyboard controller worked. So this code right here handles that. It goes out and checks to see if the repeat key's been pressed down, and if it is, then it sends the key out again, effectively. Just goes boink and does it. If it goes through the entire thing and it doesn't detect that the key is still down, it clears the array so it doesn't send more keys down, and then that's it. This is just the basic key reading process right here. That says turn on a row, or it's like read a key, turn on a row, read a column. If the column is lit, it sends it back out to the routine so that it knows. That's what all that stuff does. This is special stuff for reasons because the PIC microcontroller is weird. And this is just initialization crap that you have to do every time you start the PIC microcontroller to tell it, well, which pins are inputs and which pins are outputs and all of that stuff. So then you scroll on down here, and this is the key matrix. This is the keyboard matrix. That's it. And you can see what it does is the first number here, the first matrix endpoint, is if you press the key by itself, This is the value for press that same intersection with control, that same intersection with shift, and that same intersection with control and shift. And then it just has binary bit values for all of the bits that it has to send out. And that's it. That's all there is to it. Eric is like, can an Arduino do all this? Yes, an Arduino controller is more than powerful to do all this. I just happen to use the PIC because it was the first microcontroller I learned how to do. And yeah, that's it. What's this clown up to now? Well, that's very interesting you say that, Jay, because I do quite good for myself being a clown. So maybe you should try it sometime. So yeah, and that's just the key matrix for that controller. You can see basically these two numbers right here, the 4 and 5. That's the intersection of X4, Y5, for example. And it's at each intersection, it's defined, and then yeah, that's how it is. That's basically what it does. So that is the details of the code. So now what we get to do is we get to take a look at the Amiga, right? That's what you all really came to me to see and do. So all keyboard, here's the upside. Pretty much all keyboard controllers, with the exception of the IBM keyboard controller, which is its own special thing because it's different. All keyboard controllers are pretty much the same. They have a series of X pins, a series of Y pins, and a set of output pins with some extra control inputs, like for control, shift, escape, alt, stuff like that. And so what happens is it has a series of X rows and Y columns. It will light up an X row, then read across every Y column to see if a button gets picked up. If the button gets picked up, it can then see, oh, okay, so you've pressed the button at this intersection, which is the letter B. Cool. So then it goes, looks up that letter or what that code is supposed to be at that intersection, and then sends it on output pins and sends it out, potentially with some other control data to tell the computer, hey, I actually have data available for you. Go read the data, right? It's usually called like a keyboard strobe. They all work pretty much exactly the same way. That means that most of these generic keyboard encoders, my solution will work for all of them. I just have to remap keys and rearrange the physical hardware. But that software, with a few exceptions, is just it. It just works. It works identically every single time. There's no change. So that's what we got to do. I never actually programmed this chip. So let's do that. I'm going to show you programming the chip. How's that sound? Does that sound fun? Let's actually program it. I don't need that open. I need to do this and then do that. Cool. So I've got the chip in here, and then I go up here and I hit that button, and it has detected it, and it's giving me a glitchy error because it does that sometimes because this adapter doodle doesn't always get the chip in there correctly. That's a problem with my adapter. Yeah, should be okay. There we are. Let's try that again. Connecting to programmer, connected, low voltage configuration. It's complaining, blah, 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 blah. Again, this is this controller, or this adapter doodle is funky. I thought some primitive computers pull the keyboard while others use interrupts. There are multiple different ways to do that, Stars, actually. If you have a dedicated controller, the controller pulls the keyboard itself and then just sends data to the computer and signals to the computer in one way or another how that it has data ready to be picked up. Ah, it worked that time. Yeah, my adapter doodle is weird. Programming verify complete. So the keyboard encoder is done. We need to go back to here. So that keyboard encoder has been programmed. All programmed and ready to go. So these keyboard encoders, they're scan and set types. Basically, what they do is this is its own computer that scans the keyboard matrix and then presents to the computer the data that's on that it picked up on the matrix. These can alert the computer one of two ways. It can alert the computer through a simple set pin. Well, they're all going to alert it through a set pin. They're going to like turn one of the pins on to say, hey, I have data ready for you to pick up. Come do something with it. What the computer does with that set pin varies, right? So that set pin could be, in the case of these, what it does is it just goes, it just pulses the output pin. It's not on solid, it just goes, and it's designed to go into the computer and set a flip-flop in the computer itself that then goes into an on state. So basically this says, I have data ready, come get it. And it just lets the computer figure it out. Now that little flip-flop could be connected to an interrupt pin through an interrupt handler if you want. Or in the case of like the Apple II, all it does is turns the flip-flop on and it leaves it to the programmer to go and periodically check that flip-flop for keyboard input when the computer is ready to receive input effectively. So if you have a program that never uses the keyboard, you never have to scan the keyboard and you get a little bit of CPU time back. Because you can smash those keys all you want and the computer doesn't do anything with it. It ignores it. Others have a full, how can I say, a full like data interrupt process like the IBM. Every time you press a key, it tells the computer, you need to come get this data. If you don't come get it, it's going to be gone, right? And the computer has to have an interrupt process to go in and command the keyboard to give it the data, to fetch it. Those are usually what happens in serial keyboard processes, like with the IBM keyboard, and it pulses the data out, and then the computer will set it in a buffer for the program to go handle it. That's all handled by the BIOS or the backend process there. So yeah. So now we get to test this key, this thing in the keyboard. So we're going to do that real quick. We'll put solder aside. We're going to test it. And then we get to, ow, I just, my elbow, just smacked my elbow on the Apple II. Put this over here. We're going to change my screen to that. Get to put this in here. That goes there. This goes here. Like that. Easy peasy. Then we put you up like this. Hopefully my thing doesn't go wacky. And then we do that. It works. Top row works. That works. A, S, T, F, G, H, J, K, L, semicolon, those keys, Z, X, C, V, B, and M. N is always weird. M, those keys. Yes. And so shift works. Yep. And control works. Yep. Works perfectly. Perfectly. This doesn't look like an Amiga. We're doing the Amiga next. I wanted to show you the background of building one of these one of these controllers and all of that stuff before we actually went into the reverse engineering process. So poo on you. Poo, I say. So now let's get the Amiga stuff out. Let's do that. So let's move this back and move this up like this and do this. Because we are done with this entire test frame for tonight. It's done. It is done. Done-a-doodles. So we need to get Mr. Amiga. Amiga. Apple II forever. Okay. It's there. Amiga keyboard. Where did I put it? It is down here. Stand by. Oops. I forgot to take my meds. Look at that. Amiga 500. Hey, fan geeks. Hey, Alex, how you doing? Can gal and pals be reverse engineered? You're talking about gated array logic or generic array logic and programmable array logic. They can, under certain circumstances. Generally, in all circumstances, they can be reverse engineered. It depends on the gal or pal in question, and the effort required depends on multiple factors. I need to run upstairs for a half second. Bruce! I always have to do this for Bruce. Bruce. I need to run upstairs and get my meds real quick, and I need to get myself a nice, another tasty Diet Coke. You get to hang out and watch the screen for a half second while I do that. Stand by. Sorry about that. I'm back. I'm here, I promise. Hi, everybody. Sorry about that. You turned up for the exciting bit. Yeah, we get to like do the reverse engineering stuff. Yeah. I'm gonna switch back to this camera for a half second. So yes, I take medications. Many people do. I'm not afraid to talk about it. I've talked about it several times. I have generalized anxiety disorder. I get anxious for absolutely no friggin' reason whatsoever, so I take medication for it, and it has absolutely changed my life for the better. I use every opportunity to tell people that if you need help, go get help. Don't be afraid to ask for it. There are people out there, they will help you with those problems. Brain pills. Okay, so let us get back to what we were doing. So yes, the Amiga. Let's switch back to Benchcam. So here's Benchcam. So here's the Amiga keyboard. This weekend, with thanks to many, many helpful people, you need $50. You gave me $50 earlier. Do you want it back? So, I think Justin here in the chat as well, he was a big push for this. There were a lot of folks who are like, Joe, can you do a reverse engineer of the Amiga keyboard controller? I'm like, it doesn't already exist. They haven't made reverse engineered chips for that already. Amiga's huge with modders and stuff, but apparently they haven't. So we're going to do that. Here, let's get a little closer. Get a little closer with Arid Extra Dry. Okay. Cool. Can we adjust that? So yeah, there we go. So Amiga 500 keyboard. Simple, straightforward, uncomplicated keyboard. It's got its own little controller board and stuff on it. It's a membrane style keyboard. Whoop-de-doo, big deal. That's, par for the course. That's how they were done. Can you go back in the slots and not be stupid, please? Go like that. So there we go. That's where it needs to go. Now this has its own keyboard controller right here. It is the Commodore Semiconductor Group, also known as MOS Technologies, the inventor of the 6502. Turn that. It is a 6570. The 6570 is a very interesting chip because it's effectively an NMOS 6500/1 one-chip microcomputer. It's a microcontroller. It's a generic microcontroller. That's all it is. That's all it is. That's all this thing is. And this microcontroller is a 6502. It is the venerable faithful MOS Technology 6502 with a whole bunch of pins added to it. It's like a 6522 married up with a 6502 in one controller. It's a really weird thing. But yeah, that's all it is. That's all the thing is. It's nothing fancy, nothing complicated, straightforward. And this really doesn't matter. All I need this data sheet for is to know what the pins are, right? So that's that. Second piece of information, which is it in here? Do I have it? I swear I printed it out. I'm looking for it. Give me just a second. Nope, that is for a different project. That is for that project. I thought I printed it out. Apparently I didn't, but that's okay. We'll just go to this. The other piece of information we need is what the keyboard matrix is. We need to know when X and Y are pressed, what they equal when they're pressed. So we have that. We have what that keyboard matrix is. So with matrix like this, we can do a quick mass programming of this stuff. We would just, for these letters, for example, we just need to confirm, like when you press A, what do you get when you press A? Do you get literally like 8 bits in a row of ASCII A? You just get an A. And when you press shift, do you get the uppercase A? Like this, what does it do when you press those? So that's what you need to know there. And then we also need to know, like when I press escape, what code does it send out? Does it send out ASCII escape, which is 27? Or does it send out like 129 or some funky number? These F keys as well. What do those do? What do those send out when you press those buttons? We need to know that. So what we do is we can hook up to the controller with a oscilloscope, press the key and see what shows up on the oscilloscope, and then just reverse engineer the ones and zeros effectively, right? Joe being silly makes the channel fun and great, I think. Thank you, Alex. Yes. The only thing less reliable than MOS chips is MT RAM. Yes. 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 So I printed out a couple of these. These are just for my reference. So as I can like put marks on them as I go. These were available. Thank you again, Justin, in the chat. He helped me find those. Was it Friday night when I took on that challenge? The other thing I wanted... oh, I didn't print it off. I have it up here. I just didn't print it off. Can I show you the screen? I can show you screen cap right. Yeah. So this right here is some information I got from a website that tells me what every single pin on the actual controller is and what they do. Right. So this... I can tell which one's 5 volts, which one's ground, which one's whatever, so that when I actually connect things up, I know where to route them to on my microcontroller, right? So that's what this helps me do. And this column down here helped me add up the total number of I/O pins, which is 32. My chip has 36 input and output pins, so I have plenty of extra pins. And this tells me what we need. So yeah, we got the pins. The problem is with this is it says connected to keyboard matrix. Well, that doesn't mean crap. Connected to where on the keyboard matrix? Like where on the keyboard matrix? Which one's 1? Which one's 2? Which one's 3? Which one's X? Which one's Y? Which one's B? I need to know that. So a lot of tonight, what we're going to be doing is going through these pins. And we'll go back to Benchcam here. We're going to be going through these pins and trying to figure out where on this freaking matrix they are. That's what we need to figure out. Because until we figure out where they are on this matrix, we aren't going to know crap about crap, right? So you get to watch me do at least a little bit of boring work. Some of this work is boring. It is just boring, but it is what it is. So let's get to it. First things first. I need to get to my oscilloscope here. Get that turned on. Doobie-doobie-doo. I'm going to need a couple of oscilloscope leads, I think. Maybe 2, maybe more. We'll see. We'll get a couple. What do we need next? I think we actually have to turn this on, don't we? Can I power it externally? Probably just want to turn it on and just let it sit there. That's fine. No harm. It has to actually be running. Power? Where's my Amiga power supply? Oh, poopy. In here, Amiga stuff. Yep. Amiga power supply. Right here. Big honker. Lots of stuff in the container I have never gotten to before. Okay. Cool beans. Welcome to Joe's Boring Stream, where he connects up a computer for a long time. Let's run this back here to this power brick. Works for me. This goes in this back of this somewhere here. Big chunky connector right back here. Big Chonko connector. Connect to Chonko. Yes. That's that. And we could turn that on, but I need to. Does this one have the composite output? It does. I do have composite output for this, so I can see it on the screen and see it operate. So I know that it's running properly. Stand by. That's an RF output. I don't need that. I think I just need to plug it in to the mono output. The mono video output will probably just work. This right here. Let's flip the switch, see if it works. Sure does. Sure does. You guys can't quite see it on there, but there. So I got video output here. Cool. So I know that the machine's working. Amiga 1.3 workbench. Put in a disk. Do the thing, jerk. Great. So that means that we can press keys. And with this running like this, I can tap the software failure. Yeah, whatever. I don't care. I can tap into the keyboard down here and do the thing. 630 Joe, no problem. Cool beans. Sounds good. Now, let's figure this out. So, with this, we can tell, I showed those instructions and it didn't say where on the keyboard matrix they go. But this does tell us that. You can't see it! This actually does tell me which one's X and Y and all of that stuff. So we can go down through here and label these and say what pin is what. But what we really need to do is do some basic intelligence work. What we need to do is figure out where the output pins are on this controller, connect it to the oscilloscope that you can't see right now, and press some of these keys to get an idea of what values this thing puts out when I press those keys. Now, a lot of that is going to be, honestly, me off camera later, pressing keys one by one and typing in every single binary code for like hours and hours and hours to figure out what it is. In theory, I could create some sort of like Arduino thingy-mabobber that connects to this, that gives it inputs and then reads the outputs and stuff, but I'm not going to go to all that work. But yeah, so that's basically what we do. So what we wanted to do is we need to figure out the data output lines. The data output lines, according to what Amiga series this is. This is an Amiga 500. I wanted to do the thing. Was that workbench booting? No, it was asking for the workbench disk because this doesn't have workbench built in. Processing data. This is like, yay! Thank you, Justin Morgan. This is a bog standard, completely plain, literally, a completely out of nowhere Amiga. It has nothing on it. It is literally like an out of the box plain Amiga. Processing data. What was I doing? I was going to this sheet here, and I'm actually going to print it if I can. Yes, I can. RAM part for Joe. Thank you. I didn't want to do that. You need to go like this, screen. Stop being weird, window. Stop it. Why be weird? Window, be weird. Being weird, window. Rudy! Woo! Thank you! You guys are the best. You help me keep going. keep getting the stuff happening. So let's get this data sheet. Data sheet. Normal view. Okay. So this data sheet tells me that we are looking at the Amiga 500 side, and it's these two pins right here. So we can go all the way over here and get this pin real quick. So we are dealing with pins 37 and 38. And pin 37 is the data, and 38 is the clock or clock and data. It's these two here. So basically, I need to be on pins 37 and 38 of this controller. So we're going to do that real quick. Do I accept rubles? Sure, I guess. So let me get my little micro grabber doodles and see if we can use these. Will these work? Probably. I want to use little micro grabbers because they don't interfere with each other on this. I need another little wire like that. Cool. Barney Rubbles. You're funny. So we need to go to pins 37. So it's 40. 40, 39, 38, 37. That pin there. I can get on it. I know I'm in the way. Stand by. That's 37. See, and it's coming off. It's falling off there. I may have to partially deconstruct this keyboard. We'll see. It really doesn't want to go on there. Yeah. So I may need to unscrew this. Let's unscrew it. Let's do it. Unscrew the little screws. Put it in this container over here. There's one final screw here that needs to come out. And that should come out. And then we snip this thing right here. This little zip tie. Get it out of the way. Get that out of the way. This should allow this to kind of come out and flip down so I can get to it a little better. Maybe. Let's see here. There we are. That should be a little easier for me to work with. Yes, it is. So let's prop some stuff up here. Let's put that in there like that. It's not going to fall. Nope. It's pretty solid. Now I can get to these pins. Cool. So I need to be on 37, which is this one. That's on there. And I need to be on focus, you feck, right? Okay. 47 and 40, 37 and 38. These two. Right next to each other, right? This other one is... Oh, stop doing that. You go here. Stay on there. Cool. So then we can pop these little pins in here so I can grab it with my grabbers. That goes there. That goes there. And which one is clock? Clock is 37. So that's this one. Clock is going to be my trigger. That's going to go on here. And data is going to be my data. Like that. And then I need to ground this to the chassis somewhere. Somewhere like, I don't know, right here, maybe. There we are. Cool. Awesome sauce. So now we can turn this on and see what happens. Cool. So we can set our trigger points into single. so I need to go to mode, figure out my trigger modes here. Stand by. Auto. I don't know, so that's fine, whatever. I just got to figure out how to do this. Stand by. I don't use my oscilloscope that often. Maybe we can change screens so you can watch me do that. Watch me futz around with the thing. So I need to figure out how to change my trigger mode. It's not that way. I think it goes here. Nope. Measure. Source. Yeah. Cursor. Nope. Where is my trigger mode? If anybody knows the Rigol DS1054 and can remind me, here is the trigger. Here's the trigger menu. Edge. We want it. Yeah, we want it. We want it as edge. Works for me. The source will be channel 2. And we want the slope to be a falling slope. Yes. So be on the falling edge. So effectively, when I press this, you can see stuff kind of show up on the screen there a little bit. So what I need to do is do a single shot. And then when I press it, it captures it and I can see it. And so I can like zoom way in and I can see data. Cool. Yep. So that allows me to capture data. And we can look at this. Maybe I can get you all super zoomed to show you this. I don't have magical outputs or anything for my oscilloscope here, for my silly scope. There we go. You can kind of see that. So what we can see by this is you've got the blue line is the data line or the clock. So basically these are high all the time and the clock pulses down to say pick up the value that happens to be on the pin. And so every time we look at this pulse, we need to see the value that's on the pin. So I don't know which key it was that I pressed, but basically it's going to be 1, 1, 0, 1, 1, 1, 0, 1. And that was 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. Yep. So we can hit it run mode. And then say if I press F1, is it going to capture it? I know I need to put in single mode. That's right. There's the capture. And so we know what the code for F1 is. If we single shot it again and press escape, I can see the value for escape. I single shot it and I press, I don't know, the A key or this weird Amiga command key. I can tell exactly what the value is. And there you are. And that's it. That's it. That's all there is to it. Now, if I had a logic analyzer with my Rigol, or my Rigol, as I call it, I would be able to actually press the keys and like data log the whole thing, but I don't have that. So most of what I'm going to be doing is doing some basic correlation of certain things. For example, when I press Q without shift, what code do I get? Then if I press Q with shift, what code do I get? When I press Q with all of the combination of these different keys, what codes do I get? To determine, okay, so the regular keys are just plain Jane, how can I put it? Excuse me. They're just plain Jane ASCII data, which means, okay, that data is easy to fill out. But then I can go back and do the thing where I can press the F9 keys and the F whatever keys to figure out what the scan codes are exactly. Are those the scan codes you get? Yes. Those are scan codes. What you're seeing right there is the scan code for whatever I pressed last on the keyboard. Yep. And so what you see is the blue is the clock line and the yellow is the data line. So basically what you do is you read the value visually when that clock line is low. So at this point, basically at this point right here, the clock line is low. That's blue. So we read the value that's there. 0. The yellow line is at a 0. 0, 1, 1, 0, 0, 0, 1. That's it. Is it MSB first or LSB first? I don't know. I don't care. All I have to do is write it down in a spreadsheet in the order that I want to read it in. And then I can do data processing on that later if I find that I need to store it in the encoder chip in a different format. That's all that really matters. Like the data, the raw data that I'm seeing on that screen is the only thing that matters. One thing that may matter is right when you press this key the very first time, you can see that the data line goes low for a pulse. That data line going low for a pulse might be an attention or a way to trigger an interrupt on the computer itself. So I have to make sure that when I'm doing this, every time a key is pressed, the first thing it does is it sends a tiny little pulse there on the data line, not the clock line, waits a period of time, then clocks the data out. So, yeah. This is how Compaq reverse engineered the IBM BIOS, pretty much. Yep. How does it squiggly translate to 1 and 0s? Yes, I explained that. Yes. Yep. That's basically all it is. So this is effectively this kind of encoding format. This is SPI or I2C. It's the same gosh darn format. Basically, what you do, you have a data and a clock line, and you set the data to the way you want the data to be. Then you pulse the clock line, and that means that by the time the clock line has pulsed, the data is already at the level that it needs to be. And that clock line is then tied to an interrupt or something inside the computer that says, the moment that this pulses, read it now. You better read this right now. Because by time I come back and do it later, it's going to be different. So it gets its attention. Read it right now. Read it. That's basically how it does it. Bit banging. Eric Rangel. Exactly. Bit banging. Which, when you think about it, it's all bit banging. What we've done is just added layers of indirection and programming on top of it to make it easy. But when you get down to the lowest level of it, it is literally just everything is bit banging. It's just like smack these bits on and off and at billions and billions of times a second. That's all it is. So this is basically how I'm going to reverse engineer this chip. I hook up my oscilloscope. I look at the screen. I kind of figure out. I can even go in with my measurement tools. Here, I can show you. So we can go over here. I can zoom way in, right? And I can see, with my measurement tool, you can see these two white lines here. I can get way in here and see what the width of this pulse is. So I can go to cursor, select that one. So I can, so I need to do this way, stand by. So I can move this cursor left and right. And so I know that right there is the width of that pulse. And then I can go up here and I can see that subtracted from that right here, the BX minus AX, it is 19 microseconds wide. 19 microseconds. So I know what speed it has to bit bang at. So I know how long each of these pulses needs to be on. Right? That's it. That's all it is to it. I'm willing to bet there's probably, because this is a serial bit banged protocol, I'll bet you there can be quite a bit of variation in the timing. I'll bet it can be super long. If my controller can only bit bang at say 40 microseconds per pulse, it will probably work just fine, because the Amiga is going to sit in a tight loop, effectively waiting for a bit to come in when that signal goes low. So as long as I set the value I want, pulse it, change the value, pulse it, change the value, pulse it, my pulses are no less than 19 0.2, it'll probably work just fine, no matter what speed I did. That's it. That's all there is to it. So, yep. And then I can do other things too. Like I go in here and I would position. So this primary pulse right here on the data line, we look at this pulse, right? And we see that it is also 19, approximately 19 microseconds, right? It's the exact same size. And that comes in, then we can go out like this and then do this. And we know that it will come in a minimum. So let's look at the first data pulse, or the first clock pulse. And then we move this over here. We know that it's got to finish 146 microseconds before the first clock pulse. So we can do timing like that to make sure that we're within some sort of normal timing spec. And so we just write all that down and start to do it. So how would I start to do this? Well, the first process is going to be writing down all these little specifications, right? I'm going to write down every key that gets pressed. Let's go into single shot mode again and press, I don't know, the D key. And we can see every single time it's got that tiny little data pulse prior to the clocking of the actual data. So we can single shot it again and press, I don't know, the asterisk up here. It is exactly the same every time. So that's our protocol. That first tiny little pulse is probably an attention pulse or an interrupt pulse or something that tells the Amiga, hey, I have data coming in, you need to deal with it. So we need to make sure that every key press is preceded by that pulse. Then we can clock our data out. So I write down all those specifications for the timing, and I just kind of create a little timing map, right? And then what I would do is I would sit here with a spreadsheet and write out the key matrix. Standby. We'll change our screen so you can see what I'm pointing at. So I would take this key matrix right here, this or this, and lay it back out in Excel as a grid, right? And for every single one of these buttons, I would press the button and write down the bit value in that Excel spreadsheet. And as you can tell, that would take a really, really long time. So I'm not going to do that on stream unless you want to watch me write Excel spreadsheets. So then I would write every single one of those values down for each key press. Then I would go through and do a couple of other things, a couple of other tests before I do that. I would try testing each key. Jesus Christ. Dude, you guys want to see this? You want to see this? Look, look, look. Do you see him? Do you see him on top of my scope? We have a friend. We got a little friend on my scope. Hi, scope friend. Just go back there. Thank you. Stink bugs. Little stink bug. Won't hurt anything. I actually like the smell of stink bugs. I'm weird. Anyway, so what I would do is I would do some tests. So like, let's put this in single shot mode. I want to zoom it out a little bit. There we are. So let's press the letter Q. So the letter Q is, I can actually just write this down real quick. So it's 1 1, right? So it's 1 1 0 1 1 1 0 1 1 1 1 1, right? Now, what happens if I press that with shift? Is it this exact same code? Single shot. Interesting. When I press shift sends its own data out by itself. Careful that Q doesn't show up to alter the space-time continuum. The trial never ends. Yes. Nice shirt, by the way. Thank you. This is my Dark Side of the Track shirt that was designed by Will Wheaton. So this is interesting. This keyboard, keyboard sends out a key pulse for every key you press, no matter what. So the shift isn't necessarily a modifier key. It's just a key like anything else. So this keyboard works a little bit more like the, how can I put it? It works a little bit more like the IBM keyboard does. So when you press shift on the IBM keyboard, it doesn't change the value of the the key Q. It just tells the computer Shift is being held down. So the computer can deal with that. It's also cool, too, because it allows you to read every key in the key matrix. Period. That is very, very nifty. And if we look at this, right, I'll show you here on the screen. We'll show you. So if we look at this here, you can actually see that the left shift and the right shift have their own data lines. They're not in the array. So they're not modifiers in the same sense. So that means you can even see here too, this indicates that each key is individually addressable because the left shift and the right shift are detected independently of each other. So that's cool. Same thing for the left Amiga and right Amiga keys. Which one is which, I can't tell by that, but we'll figure it out. So yeah, cool stuff. That may actually make this easier because that means every key only has one key code, right? Pretty much. Yeah, that makes this really, really easy to do. Cool. A lot less to do. So basically, that's what the process is now. You're going through every key, setting up the trigger, pressing the key, typing it in a spreadsheet, repeat for however many keys this is, some 100 or some keys, and that's it. Is there a data packet for key release? That is a good question. So let's put it in continuous run mode. So I'm going to press a key down and hold it, then let go of it and see if we can capture anything. There is. So that's a thing we need to check for as well. So if I press we can put it in single shot mode, press the key, single shot it again, and it should stay run. If I let go of it, it sends a code again. So it does have two codes. Interesting. So we do have to account for that. So instead of being a key repeat process, instead in my code, basically it's constantly scanning the keyboard all the time, no matter what. It's in a constant loop, and it determines what key sequence to put out based on how long the key has been held down. Effectively, the auto repeat function. Well, in that piece of the auto repeat function, instead of checking to see if the key is still pressed down, we check to see if the key is pressed up, has been pulled up. And if it is, we send a second code. So we send one code went down, one code went up. And that's it. Yep. So that is very, very interesting. The Apple II had to change circuitry when the mouse came out because it needed to detect shift clicks. Yes. Yes. If you test 4 keys on the same row, would you see a pattern to make this easier? The 8th bit is a flag to indicate whether the key is going down or up. Is it? So let's see. So let's put it in single mode. We will do Q. So we know what that is. That is 1101 1111. We single shot it. And this time it was 1101 1110. You are correct. Good. That is nice. So that means I can use a single bit array, or a single how can I put it? Yeah, a single key map. So I don't have to have all 256 values programmed. Only have to have 128 values for 7 bits, and then the 8th bit is just turned. I send it turning on or off, whether it's up or down. Cool. Awesome. Easy. Nice. Good catch. Thank you, Gregory. The 8th bit is a flag to indicate. How did you know if the 8th bit was a flag to indicate whether the key is going down or up? Do you have information on how the keyboard controller works? Because if you do, I'd like to talk to you. Because if you have enough data, you might make my job easier. But that's fine. So yeah, if you test 4 keys on the same row, would you see a pattern to make this easier? Probably not. Each key is probably its ASCII value. That would be my guess. But it might not be. It might just be literally like button 51, 52, 53, 54. So I'm going to go to ASCIItable.com, which is how I looked this up. And when I pressed Q down, it gave me 1101111 effectively. So if I look at the value for Q, which is decimal 81, and we go and we do some programmer stuff here, and we go to decimal 81, yes. It doesn't really correlate either inverted or directly to the actual button pressed. It's like completely different. So it looks to me that this matrix is just a matrix in a row. So if I press 1, it looks like it's 1. It's literally just that bit. So if what's the next key? It's this one. Yeah, it is. They're literally numerically in order. So if I press the escape key in the upper left corner, well, that doesn't really correlate to anything. It doesn't seem like there's a direct correlation, but there is some sort of, so that's Q, which is just that. Yeah, and W brings in this bit. And that's the next bit over, and that's 2 bits in a row. So they are in numerical sequence. So that makes it really easy. So it is they're just key codes. They're literally, or they're scan codes. So it's 21, 22, 23 as you go across. It's 21, 22, 23, 24, 25. So that does make it a little bit easier. Now the upside with that is that means I can smash program the crap in there and write a little Amiga program, for example. In Amiga Basic or something that shows me the key codes, and then I can test it to make sure that when I'm pressing Q, it actually shows a Q and stuff like that to do some final testing. But yeah, that's nice. Cool. Awesome. That makes things a lot easier. In programming, there's usually a key code and a key ASCII, yes. Cool. Amigas are completely foreign to me, so I'm just here to build stuff for the community. Somebody asked, Joe, can you do it? I'm like, why couldn't I do it? Well, it works the same way as every other keyboard controller, other than the codes it sends out. So basically, the only thing I would need to do here is map this key code sequence and change the output code so that it A, outputs when you press it, and B, outputs again when you pull it up. And it has to keep track of how many keys are pressed down simultaneously. So it's going to have some internal memory to keep track of how many keys are pressed down. And I can use the same matrix that I've used before to determine if a key is pressed down for key repeat purposes. So if it scans and sees it's already down, it just leaves it down. And every time you pull it up, it unsets that in that secondary memory matrix. Yeah. And basically, and that's what we can do. That 8th bit will literally just be the value of that matrix when you send it. Yeah. Yeah. Piece of cake. Easy peasy. Super easy. Easy. It's just a lot of manual work. So that's basically all there is to that. So yeah, let's take a look at the code, and I'll kind of show you what I plan on doing. I need to go to screen cap right and show you like the windows into forever, and go here. So if we look at this code, basically all of this would be pretty much exactly the same. These keys right here will be a little bit different because there are many other input keys. It wouldn't just be shift and control. We have specific pins for left alt, left shift, left alt, right alt, control, open Amiga and closed Amiga buttons. So those would each have their own input pin for the thing. Easy peasy. But then the rest of these keys would be defined by the matrix. The loop code would be pretty much the same, with a couple of sections. First off, the key out function is going to be different because what this key out does right now is it determines the row and column by reading in the control keys and the shift keys to determine which key to send out. I don't have to do any of that. I don't have to do any of that at all. All of this complication goes away, and all it's doing is it's going to send the row and column code out. Or it's going to construct the row and column code based on that. And then the final bit will be this bit here is the which key. Because this array, if the key is pressed right now but wasn't down last time, this code right here, it means send out it's being pressed down now. And else, here, what it will do is, oh, you've released the key? Well, it's going to send the code out again, but it's going to send the key up code, which will be this exact same code plus this equals 0. That's it. That's all it does. And the rest of this is going to be pretty much the exact same, with the exception of this a key was down stuff probably does in the repeat code for this particular controller that I'm using as an example here would go away. I wouldn't need all of that. The key out process will be pretty much the same. Nope, this will be different. So what this does, this is designed for these parallel keyboard controllers. Basically, it lights up all the bits all at once, and then it pulses the data ready line to tell it to do it. For the Amiga, it's going to be different. This effectively would go at the front here, up here, and we pulse the data line once. We delay X amount of time. Then we send, basically it's a loop of set bit value, turn clock on, turn clock off, set bit value on off, bit value on off, bit value on off, all the way through. Then the very last bit is you're sending the which key value to tell you whether it was down or up. And that's it. That's it. You've been trying to post a link to all of the keyboard documentation for the Amiga. I'm guessing that's not getting through to the chat. It is not, Gregory Brady, because you are not an admin, which does not allow you to post things. However, I can make you an admin and let you post things as long as you agree that you're not gonna be mean and post things that you can't do. So I'm gonna click this and do that. You are now technically a moderator for my channel. So if you have a Linkadoodle that you want to send, hey, look at you can see all my backend stuff. If you have a Linkadoodle you want to send, you can send a Linkadoodle. Facecam. So yeah, should be able to post that there now. If you see a little wrench next to your name, it should allow you to do it. Linky Doodle. Hi, Bruce again. How you doing? Rudy, can you make a hit that like button app? Sure. So yeah, that's pretty much all this is going to be. That's the cool thing too, because people have already made replacement USB encoders for you to plug in USB or PS2 keyboards. All of this work has already been done as well, right? That's already been done. So the entire key matrix has already been done. If somebody's already done that, I can literally copy and paste that code or that table straight in without having to do all of the manual reading work, right? That saves me a lot of time too. I'll do it manually if I have to, because I have the tools to do it. But if somebody's already done all the reverse engineering work, why would I redo it? Has all of the matrix and scan codes as well as oddities like how control Amiga works. Yes, that's going to be important as well, because we need to know how that sends out a reset signal to the machine. Very important. Yes, Gregory Brady, you are now an admin or a moderator. You have a little wrench next to your name. So that means you can post a Linkadoodle to that information if you like. Yes, Bruce was on stream last night fixing lots of super awesome, cool stuff. And he was talking about having to go out and get fancy clothes to go out to some sort of fancy dress attire thing. So yeah, done above. Done above. There it is. Link. Yeah. Cool. Is chaotic good allowed for mods? Yes. Yes. Cool. That is awesome. That is super awesome. Gregory, you're going to get thanks in the source code. I need to make sure that I copy your name real quick because of your help in helping me get that data. So I'm going to note your name here real quick. Notepad book. Helped me find the key code data. Yay! Thank you very, very much. That is super helpful. So that's basically what we're going to do at this point is go through all of this data. I can show you that screen. Right. This is all of the data. Keyboard plugs into the Amiga computer via cable with 4 primary connections for us, provide power, ground, and signals called keyboard clock and keyboard data. Keyboard clock is unidirectional, always driven by the keyboard. Keyboard data is driven by both the keyboard and the computer. Important to know. Haha. Both signals are open at collector. There are pull-up resistors in the keyboard inside the keyboard microprocessor in the computer. So yeah, so it does work, but it is multi-directional. So we can go to keyboard communications, and it tells it how it pulses. The up-down flag. Yeah. In order to cause a key upcode to be transmitted in case the keyboard is forced to restore lost sync. Some fancy stuff that we have to do. Key table. That is awesome. Look at that. That is so cool. Yeah. Key code only was pushed down, never when it is released. The up-down bit is still used. When pressing the caps lock key turns on the caps lock LED, the up-down is 0, down 1. Interesting. Cool. Very interesting indeed. Out of sync conditions. The keyboard receives a handshake pulse at the end of its transmission. Ah, I see. So what happens is the keyboard sends data, and then it does. It's a full bidirectional thing. So if it doesn't pick up the key within X amount of time, it keeps doing it. Got it. Cool. Hard reset. Initializes the keyboard. The keyboard's got to get power up key stream, power up sequence, blah, 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 blah. Wow. Lots of little things that we have to kind of account for. Okay, cool. So it's not just it's a lot more complex than I thought it was. But the upside is my controller has enough because the key matrix is going to be a lot smaller. It's basically going to be effectively about a quarter of the size. I've got a lot of extra RAM space. So if you look here, my data space isn't very large right here because of this gigantic freaking key matrix. It's huge. But it's going to be a quarter of that size effectively. So I'm going to have a lot more space to deal with these different cases. Cool. So one of these pins is going to be interesting. Interesting indeed. Interesting stuff. Reset warnings. You cannot rely on this feature on all Amigas. Yeah, so there's different versions that do different things. Reset warning. Self-test failed. So we have to make sure when we turn it on, we send these special bit sequences. Sweet! Gewürztraminer ice wines are freaking awesome, by the way. They are good. Ice wine. Yes. Oops, you don't need to see my screen. You don't need to see that. Cool. Awesome. That is freaking great. Thank you very much, sir. Very, very much, Gregory Brady, for helping me get that documented data on all of that information. That is a lot better. That since it's already been reverse engineered here, I can turn this thing off here. Since it's already been reverse engineered, I literally just have to follow this document. I just write my encoder for the document. So the next thing is how we need to do a couple things to make sure that we can make the keyboard encoder work the way we expect it to. So here's how we do that. The first thing I would do is, now we have like an understanding of how the keyboard controller works. Let me switch some screens around here. That. Zoom out. Cool. So the first thing we would do is I would be adjusting this camera very carefully. Keyboard encoder. So what I would be doing is I would be very carefully taking this keyboard encoder out of this contraption here and putting a socket in there so that I can swap between the original keyboard encoder and my test encoder. Right? Did you see sample 88? Did you see that? I have sample 88. Yes. I have version 1 of sample 88. Bruce has version 2, the final version. Once I've taken that out and socketed it, that will allow me to put the encoder back in and out several times and all of that stuff, right? And then I can make a jig like this thing, that I can put into that socket with the full 40-pin version of my chip there, which is easier to program and get in and out. I don't have to, whatever. Basically, this is a big wire wrap version of a final PCB version of this, but allows me to manufacture this test jig so that I can put the chip in, test it, take it out, reprogram it, put the chip in, test it, take it out, reprogram it, then keep doing that until I've iterated through all of the edge cases and using this documentation to say, okay, when I press this key sequence, does it follow the documentation? When I do this, does it follow the documentation? When it turns on, does it receive its startup command correctly? Does it do this and that and the other and all of that stuff so I can test all that stuff? And once I've tested that, and once it's working in this test jig completely and correctly, 100%, I know the code is final. Then what we do is we go over to a program like this. That is the wrong program. I will show you the programs shortly. Stand by. I would go over to a program like this, Sprint Layout, and then you would have, I could then create this layout of a PCB. I can create the PCB to fit my small form factor of the chip and to get the pins where they need to go and put pull-up resistors where pull-up resistors need to be, and this and that and the other to do all of that. And then I can send this off and spin it out to, a manufacturer, get it in, build one up, stick it in there, and if it works, it's done. It's done. That's it. Pretty fun stuff. So that's how we do it. Yeah. I have formula CH4. Methane? Are you saying that you ate beans earlier? Migraines, rosacea breakouts. Yeah. Red wines. Yeah, it's a different thing. Yes. I'm not an alcohol person at all for the most part. It interferes with that medication I talked with earlier. It can, best case, it makes me basically turn into a complete like zombie who wants to sleep constantly. It just knocks me out. Worst case, it can actually cause a depressive crash in which I don't want to do anything for like 2 weeks. I turn into it undoes my medication. It just shuts it off as if I hadn't been taking it. So I can't really drink alcohol. I love me a beer though. I like good, I call them sweet beers, malty beers. So I like my ales. I'm not an IPA guy. So yeah. And I will volunteer my Amiga 1000 keyboard for testing. Yeah, cool. So basically at this point, because I've got this setup done. Yes. That. Now that I've got this all laid out, right? And I have this figured out. All I have to do is go through and program a chip and do a thing. And do a thing and do it. Let's get reverse engineering. Come on. Jay, do you want to like sit here and watch me for the next 2.5 to however many hours it's going to take to manually write in a whole bunch of binary codes into an Excel spreadsheet and then copy and paste that into a programming? Do you really want to do that? Seriously? That's the boring part. I've already told you what we need to do. It's at this point, it's a lot of manual, boring work. But basically, we just use that documentation, that documentation that Gregory Brady sent us, and do the thing. 12 hours, no problem. Let's do it. No. That's a boring thing. We're not gonna get into all that. But yeah, let's go back to this documentation. I want to read through it again real quick. Screen cap rate. So can I zoom in? Yeah, we can zoom in so it's easier to read. Primary connections, keyboard communications. Okay. The keyboard must be able to detect pulses greater than or equal to 1 microsecond. Wow. That is some crazy fast timing. We can detect that with a reset or with an interrupt. That's not a problem. Yep. 85 microseconds, fine. Codes transmitted to the computer rotated 1 bit before transmission. Interesting. The transmitted order is therefore 654321007. Gotcha. Okay, that doesn't really matter. To cause the key code to be transmitted in case the keyboard is forced to restore lost sync. The KDAT line is active low. That is, a high level is interpreted as 0, and a low level is interpreted as a 1. Fine, whatever. That doesn't really matter. Keyboard processor sets the KDAT line about 20 microseconds before it pulls. K clock low. K clock low stays for about 20 microseconds. 17 kilobits per second. Yeah, whatever. That's fine. Cool. Key codes. So with the key was 7 bits long, the 8th bit is key down code. Caps lock key is different. Yeah, it's basically it's negative logic, but that doesn't matter. All I care about is the actual bit sequence. I don't care what's an actual 1 or 0. It's like what electrical signal is being sent, and that's how I'd encode it in the table. B is released. It's exactly the same thing, except it's got that. Caps lock key is different. It generates a key code only when it is pushed down, never when it is released. However, the up-down bit is still used. When pushing the caps lock key, turns on the caps lock LED. So you push it. When you push it down and release it, it's like it's a down bit, and the other way is an up bit. Okay, cool. Out of sync condition. This is very interesting. What is this handshake pulse? Doesn't really discuss the handshake pulse specifically, does it? Keyboard transmit 8-bit data words. Keyboard starts transmission by first putting out the first data bit, followed by a pulse on K clock. Yep. When the computer receives the 8-bit, it must. Here's the handshake. Yeah. It must pulse KDAT low for at least 1 microsecond. The handshake detection on the keyboard will typically use a hardware latch. That doesn't really matter. The keyboard must be able to detect. Yeah, fine. Software must pulse the line low for 85 microseconds. That's fine. Cool. Transmitted the computer rotated 1 bit before transmission. Yeah, cool. So that's fine. Got it. Excellent. Here's the thing, like, remember we were seeing on the screen. Here's the thing that confuses me. Zoom your way in. So how many pulses on the screen here? We have 1, 2, 3, 4, 5, 6, 7, 8 pulses. Now, if we look at this, how many pulses do we have here? Yeah, we've got 1, 2, 3, 4, 5, 6, 7, 8. That's fine. But we have this initial pulse here. What does that mean? That's not the handshake pulse, because that should be coming afterwards, right? This should be being sent by the keyboard, and then we should have another pulse back here that's sent back out by the computer. Interesting. So it's not showing that pulse on here anywhere, right? Let me read the chat real quick. I'd like to see a walkthrough of the code someday. K-Pro Joe, Tom Barber, how you doing? Yay! Bruce is sending you a new chip. It's not a keyboard, it's a modem. Basically, yeah. Now you see why I send you money. This is complex, yes. People have lost the art of communicating simply and directly. What if you type faster than 17 kids? I'm just going back and reading your comments while I was doing things. 20 microseconds as confirmed with the scope data. Yep. Fine. Maybe it's only a glitch pulse. I mean, it could be a glitch pulse, yeah. It could be. It very well could be. Keyboard has the additional task of resetting the computer on the command of the user. The user initiates reset wording by simultaneously placing the control key and 2 Amiga keys. The keyboard responds to this input by syncing up any pending transmit operations. The keyboard then sends a reset warning to the Amiga. This action alerts the Amiga software to finish up any pending operations. By syncing up any pending transmit operations, what I think that means is that it goes into a special mode and keys up everything that's sitting there. Yes, the keyboard then sends a reset warning to the Amiga. This action alerts the Amiga software to finish up any pending operations and prepare for reset. A specific sequence of operations ensure that the Amiga is in a state where it can respond to the reset warning. The keyboard sends 2 actual reset warning key codes. The Amiga must handshake to the first code like any normal keystroke, else the keyboard goes directly to hard reset. Aha! Got it. So basically what this is if the Amiga doesn't respond to the first reset warning, the keyboard is going to assume that the Amiga is frozen. And so then it does a forced reset. That makes sense. On the second reset warning, the Amiga must drive KDAT low within 250 milliseconds, else the keyboard goes directly to hard reset. Got it. If all the tests are passed, the Amiga has 10 full seconds to do emergency processing. When the Amiga pulls KDAT high again, the keyboard finally asserts hard reset. If the Amiga fails to pull KDAT high within 10 seconds, hard reset is asserted anyway. So basically what you're saying is the keyboard is in control of reset, period. That is fascinating. Pulling K clock low and starting 500 millisecond timer when the moment the key is released and 500 milliseconds pass, the keyboard will release a K clock. 500 milliseconds is the minimum. K clock must be held low. The maximum K clock time depends on how long the user holds the 3 reset keys down. Circuitry on the Amiga motherboard detects the 500 millisecond K clock pulse, which is basically there's a reset or there's a watchdog timer, a watchdog circuit on the Amiga that's watching that for that specific indicator that is independent of the software, so it can do the reset. After releasing key clock, the keyboard jumps to its startup code, internal reset. This will initialize the keyboard in the same way as cold power on. Note the keyboard must resend the power up key stream. What is this? Yes. Handle either case without causing any upset. First thing, you want to self-test. Yeah, I don't care about all that. It must not transmit anything until it has achieved synchronization with the computer. The way is by slowly clocking out 1 bits, as described above, until it receives a handshake pulse. Okay. The keyboard is plugged in before power up, so we can do this part during the initialization routine. So, for example, what we have here is we've got this is it at the bottom? Yeah, we have this init routine where I'm initializing the PIC microcontroller. So on power up, basically we reset all this, and then I can effectively, after we set that key map, right? No, it'd be a init pick is a init pick. So it'd be a init pick, then there would be another routine that would be warm, just call it warm reset, where we would set those. Got it. Okay. Cool. Keyboard plugging before power up. The keyboard may continue this process for several minutes as the computer struggles to boot up and gets running. The keyboard must continue clocking out ones for however long is necessary until it receives its handshake. Okay. If the keyboard is plugged in after power up, no more than 8 clocks will be needed to achieve sync. In this case, however, the computer may be in any state imaginable, but must not be adversely affected by the garbage character it will receive. Okay. Again, because it receives a key release, because it's getting a key release signal, not a key down signal, the damage should be minimal. The keyboard driver must anticipate this happening and handle it, as should any application that uses raw key codes. Fine, great. That's not our problem to deal with. Got it. Okay. This is basically a handwritten whatever. Once the keyboard and computer in sync, the keyboard must inform the computer of the results of the self-test. Interesting. Well, we would never be sending that out because I would never fail. Right? Beautiful documentation. You are right, Eric. This just literally tells me exactly everything I need to know. This is effectively a data sheet for this processor. Because the processor itself, because it's a raw processor, somebody had to internally document this, because every time they came by and designed a new Amiga, if they needed to modify the functionality a little bit for a new model, they needed to have a solid function for that, right? Why does this face cam not work? Ha! Now you can see me. How's that? Cool. Anyway, so yeah. Of course, my self-test is always going to pass because this controller is not going to fail in that, and it's not going to fail that way. Initiate power-up key stream followed by the key codes of all depressed keys. After all keys are sent, a terminate key stream code is sent. Finally, the caps lock key LED is shut off. This marks the end of the startup sequence, and normal processing commences. The usual sequence of events will therefore be power-up, synchronize, transmit, stream, transmit, terminate key. Initiate power-up key stream. Cool. Interesting. Neat. Isn't this a bit over-engineered? No, not really. It depends on how you want to define over-engineered. When you think about it, how can I put it? This keyboard the Amiga is a more complex computer, right? It has a fully preemptive multitasking operating system that needs to deal with a whole bunch of weird edge cases and stuff. And from day one, it was designed to be more advanced that way. So the keyboard has to be a little more intelligent to be able to handle that kind of operational mode, if that makes sense. So the keyboard has all of the synchronization stuff it does because it can never assume that the computer is always in a state where it's ready, right? It has to have this kind of weird asynchronous communications protocol to some extent. Or actually, it's technically synchronous, but it has to have this handshake type communications protocol because it can never assume that the computer is ready. So to some extent, it is over-engineered. But it does have many advantages over many other keyboard controllers. My standard keyboard controllers, all they ever do is it detects that the key is down, sets the output bits to be the value of the key, and then pulses a little pulse to say, hey, the key's down. But what if you want to detect when a key is released? Those keyboard encoders don't do that. They don't tell you which key is released, right? This as well, so yeah, basically it's just like an IBM keyboard in that it will tell you when it's down, but it'll also tell you when it's up. And it also sends the keys as a key matrix index. So Q is always it's always 21. Or the button in that location is always 21. That allows me as a programmer aftermarket to say, add a language pack to the computer and say that Q is actually A. Allows me to directly remap the meaning of keys programmatically in software. I can change whole keyboard maps. Like say I want it to be Dvorak or European or Japanese or whatever. All the keyboard needs to do is say, the keyboard in matrix location 2,6 was pressed. It's up to the computer to know what the hell to do with that. Right? That's the point. So that's why it's programmed that way. Yeah. The Atari ST, yeah, that's, yeah, mm-hmm. Yep, exactly. Yeah, that's, One could send programs to the keyboard controller and execute it over there. Yes. Yeah, the Atari was its own thing. The video controller was that way as well. The video controller was its own little computer. It had display lists, but basically when you sent it a display list, it was running its own code. It's like, hey, a video, go do that. I need to go do something else, and it did the thing. Bye, Rudy. Thanks for sharing. Don't spend all that money on Diet Coke. Lol. Thanks. See you, Rudy. Delicious Diet Coke. So yeah, this is awesome. This just tells me exactly what I need to do. Like I literally take the English and convert it into program code. That's it. Go all the way back to matrix table. Mm-hmm. That is so awesome. Mm-hmm. Following table shows which keys are independently readable. These keys never generate ghosts or phantoms. Okay. Whatever that's supposed to mean. Yeah. Yep. Okay. Jeff Barnard, hello. Goodbye. I'm about ready to end the stream. Go back and rewatch it. It's freaking fascinating. Wow. Uh-huh. Uh-huh. Yep. Cool. 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 Awesome. So yeah, this again, this is crazy. Facecam. Wow. Yeah. Again, thank you very much to Gregory Brady for showing me this documentation. This makes my life incredibly, incredibly much easier, and also makes me ensure that I'm not, not missing a whole bunch of special details as far as these power-up sequences and stuff. This thing is a lot more intelligent than your off-the-shelf keyboard encoder. It's because it's more than just how can I put it? It's more than just a state machine, which is what most keyboard encoders were. This is a actual computer that is establishing two-way communication with the Amiga. So it's very important. I guess phantom keys are generated when multiple keys are pressed, causing the wires to be misread. Yeah. Yep. It's a keyboard processor, not just a keyboard encoder. Yep. Exactly. Yep. So, wow. So we went through a lot of stuff today. We showed how to do how I do my reverse engineering process at kind of a high level. Put together one of my brand new keyboard encoders for the Apple II, for the early Apple II with Datanetics keyboards. And then we dug into the layer 1 of the Amiga keyboard encoder reverse engineering process and found, again, thank you to Gregory Brady, whose name will be going into the source code as a thank you. We found that somebody's already reverse engineered the encoder for the most part. Not reverse engineered it, but Amiga incredibly well documented this encoder so that I can just program it the way the documentation tells me to program it and shove it in there and it should just work. So that is super awesome. Thank you all for stopping by. I'm going to call it a stream for tonight. A lot of people stopped by, a lot of our old regulars. Thank you for stopping in. Remember, if you like my stream tonight, hit the like button and hit the bell and hit the subscribe button. When you hit those buttons, what that does is it tells YouTube, it tells the algorithm to show my videos to people who watch other videos that you watch. So say you watch a lot of this type of video and there's this other person that watches those same videos of you, but they don't watch my videos. When you press like, it tells them, it shows them my videos, which helps promote my channel. It helps show more people this cool stuff. It's super awesome. You can support my museum if you want to by going to jcm-1.com and buying a t-shirt. You can buy a t-shirt. You can get little cool trinkets and things, my keyboard encoders, stuff like that. You can also go to patreon.com/Joe's Computer Museum, all one word. Drop $1 in the cup. You can pledge a little bit every single month. That helps me keep things funded and keep the lights on and buy bulk LEDs for projects like this. It helps me out as well. Super duper awesome. Again, thank you all for stopping by. It's been a super fun thing. And hopefully in the next live stream or soon through all my different channels, like Museum Joe, at Museum Joe on Twitter, we'll be giving you a status update on what we find out with this keyboard controller. See y'all later. Have a good evening, folks.